All right, good morning. So first of all, I must say it's a great honor for me to be presenting the work of a very large crowd of people over years. So I hope I'll do a good job at it. First a word about methodology. So we did now a classical approach using a hybrid multi-frequency likelihood approach. So on large scales we use Gaussian likelihood on maps, and on small scales we do a Gaussian likelihood approximation directly on power spectra. For the foregrounds, as has been already shown a little bit this morning, for the low L, we parameterize them at the map level, and we will marginalize over their uncertainties using a Gibbs sampler. And for the high L, we directly parameterize them at the spectral level. I will be talking a lot about validation of this likelihood, so with the different ways of doing that. So first of all, we implemented different incarnations of the same IDs, and also we validated with alternative methods to see how robust our results are. We also varied the data selection and technical choices that were made during the building blocks of the likelihood. We'll talk briefly about null tests. We'll talk a little bit more about results obtained on simulations. And I will also talk about an alternative method that was quite independent and done on foreground clean CMB maps. And also there will be a presentation of an independent analysis on cosmology with the LFI 70 GHz channel. So for the higher specific methodology, we start from mask and beam deconvolved power spectra using a classical master approach for 56 detector pairs in this 100 to 217 GHz range. We further do a data compression of those in 4 combined cross spectra. So in those, in those frequency pairs, 100 cross 100 up to 217 cross 217. In the process, we recalibrate those cross spectra within a given frequency pair. We optimally combine them using the covariance matrix estimates. And we produce inter-frequency calibration priors that will be used later in the exploration. And we also do a galactic dust power spectrum correction at that level. Then we need to specify our model for the extragalactic foregrounds. And those are done with parameterized power spectrum templates. So for the CIB clustered component, which is an important contaminant at high L, we use 4 parameters, 3 amplitudes, and 1 angular spectral index. For the Poisson contribution from unresolved sources, we directly fit 4 parameters, 4 amplitude parameters. For the SZ, both thermal and kinetic, we use 2 amplitude parameters with templates and 1 parameter for a possible SZ-CIB correlation. Now for the heart of the likelihood, we did our best to include all the known effects on the covariance matrix, including of course the CMB, the noise and its correlated and anisotropic properties, and the impact of foregrounds. We also had the possibility to do some marginalization on beam transfer function errors, using priors that are derived from simulation of measurement of beam on planets. So for the higher part of the likelihood, we use a very conservative data selection, which is aimed at minimizing the foreground from the galaxy, both spatially and in multiple space, while keeping as much as we can the cosmic variance low. So the way it's done is we use actually 2 different masks, and I'm sorry the labels have been switched. This one is CL49 with 49% of the sky being covered. This one is CL31, just 30% of the sky, or 31% of the sky being covered. So for the galaxy, we actually used the 353 GHz channel map to trace the dust emissivity of the galaxy and doing thresholding on that. For the point source mask, we use actually the Planck catalog combined sources from 100 to 353 gigahertz. And then we do a mix of those masks and with different multiple range. The idea is to take for the 100 cross 100, which is the least contaminated, the biggest mask, and keeping the variance low at low to intermediate multiples, and then going to higher frequency, going to more conservative masks, and only using the higher multiples. So here is an intermediate step, which is showing very nicely the consistency between the different foreground uncorrected power spectra. Those are just combined within a frequency pair, going from 70 gigahertz to across between 143 and 353. So what we see is that basically the foregrounds are playing an important role at high L as expected, and the most precise measurement is done by the 217 cross 217 cross spectra, and we see that there is a significant foreground contamination there that we need to take into account properly. So here's possible model decomposition using our CMB and foreground model. This is obtained here with a slightly simplified version of the likelihood. Simplified meaning the covariance matrix is a bit simpler, but it will be used extensively in doing the tests that I will show later. So where you see that the CMB is dominating in all the multiple range up to 2500, where we stop our analysis, the main contaminants are point sources shown in green here, unresolved point sources in the lower frequency parts, and a mix of galaxy clustered CIB component and unresolved sources for the 217 cross 217. All right, so another way to look at the beautiful internal consistency of this data is just to look at power spectra for different frequency pairs, and overplotted on them is the best fit lambda CDM 6-parameter model. So we have 4 panels basically comparing in the first one the 100 and the 143 spectra, and finally finishing with the 143 versus 217 spectra. So what we and the bottom panel of each plot is showing basically the residual of the spectra with respect to the best fit lambda CDM. Those residuals are dominated by cosmic variance at low L, CMB-induced cosmic variance, and we begin to see a regime where the errors are dominated both by noise and foreground residual errors at higher L. So another way to see it is just to now take the difference between the spectra. So this gets rid of most of the CMB-induced cosmic variance, but we still have actually something that depends on the frequency, which is the CMB foreground chance correlations. And those can be actually accurately predicted by the covariance matrix, and they are found in very good agreement with the measured value. So that gives you a flavor really of what is dominating the budget of errors on those difference of spectra. So now you can use all the spectra, subtract the best fit foreground, optimally combine them using covariance matrix, and that is giving you the blue points, which are our best estimate of the Planck power spectrum at high L. And overplotted is the 6-parameter fit to this model from the lambda CDM, which is very nice agreement. As I said before, the low L part is really dominated by cosmic variance, let's say up to roughly 1500, and here we're dominated by a combination of noise and foreground uncertainties. A nice way to see what is the impact of foregrounds on the cosmology is to look at the posterior correlations for the high likelihood. So here you have a large matrix showing in the upper left the cosmological parameters with one extra derived parameters here, which is H0, which is of interest. And we see that basically this part of the matrix is showing the impact of the correlation basically in the posterior between all the foreground parameters and the cosmology. So you see it's mainly white, which is good news. There are some exceptions, a slight correlation of NS, the scalar index, to point source amplitudes, but the main is actually a correlation, anti-correlation actually, of the kinetic Sonia-Zeldovich amplitude with NS. And this is expected because those have the same blackbody emissivity. But this is something where the Heil experiment can give us nicer constraints on the amplitude of this KZ components. But in any case, this correlation is completely taken into account in the likelihood. So we did a fairly heavy suite of validation tests, basically. First of all, comparing the reference CAM-spec higher likelihood with our lighter, a bit simpler Planck version of it, which is an approximation on the covariance matrix. We see a very good agreement on the parameters. That's the two first whisker plots here. The boxes are showing basically the 68% confidence level, the whiskers 95%. And then we did some tests regarding the technical choices. For instance, one interesting one is when we marginalize over calibration and beam errors, we see basically almost no impact on the cosmology. Another interesting series of tests is when we vary in the analysis the maximum multiple taken in here. So of course that is changing the data selection and has a strong impact on the width of the posterior. But again, we have coherent results between the different LMAX that we take. Another thing that we did, we varied the mass from taking only 20% of the data overall to 49%. Here again, we see a variation on the width of the posterior as expected, but completely coherent results. Another test, which is also very hard to pass, actually, is to change the to subtract all the detectors from one frequency at a time, right? And the biggest difference here in this plot is coming from the fact of removing the 217 GHz channel, and that's not very surprising. This is linked to the fact that when you do that, you remove, in terms of cross spectra, basically the almost 2/3 of the data, right? So I'll talk also later about, just actually right now, about a very nice validation work using a completely different method that has been done by the GPL team. And the idea is to take advantage of the 4 CMB component separation methods, giving us 4 foreground clean maps. And those, you can compute power spectra on them, equate them with the Gaussian correlated likelihood, add 2 parameters for the extragalactic foreground models, and in a multiple range from 2 to 2000, these are the best fit power spectra that you can do, the residuals compared to the CAM-spec best fit model. And here the residuals of the different best fit theoretical models of these 4 maps, basically, compared to the CAM-spec model. So that gives you a flavor of the accuracy we have on the theory by using a completely different methods, not parameterizing things at the power spectrum level, but directly doing the comparison, the foreground cleaning at the map level. A few things on simulated data. So here we use the full focal plane simulation that will be described in detail by Julian Boril later. It's the best attempt of including the instrumental complexity and the complexity of the signal in the sky. So here we have, of course, input values for the parameters shown in dashed lines. In red, the standard results we get for this simulated map for a set of maps, sorry, for a standard likelihood. And in green, purple, and gray, you see variations, for instance, on our foreground models. In some of them where we let the slope of the CIB clustered power spectrum completely free, another one where we do the same for the dust, and another one where we fix the slope for the CIB to a value that is not favored by the data. You see the impact is extremely small on the posterior of the 6-parameter model. Another thing that you can do, which I think is very interesting, starting again from the simplified likelihood that is starting from all the detector pairs, is doing a simulation, recovering the calibration and beam modes on simulated data. So the results should be 0 here. That's what we get at the 0.1% accuracy. The beam error modes are a bit small, have larger error bars, but they are compatible with no correction. That is what we get on the Planck data. And so we see slight recalibration, which are smaller than 0.2% in amplitude, and that's a remarkable achievement. And this is in line with the expected level of errors we get on dipole measurements for individual channel maps. Then I will go briefly, because my time is running short, I'm sorry about that, on the low L part of the likelihood. So that is taking all the maps from 30 to 353 gigahertz at low resolution. We are concentrating on the multiple range from 2 to 49 with a sharp transition with the high likelihood. We verified that the details of the transition don't have an impact on the cosmology. The maps are, as was shown before, are modeled now at the foregrounds are modeled at the map level directly. And the idea is to get directly a Blackwell-Rao estimate of the posterior distribution of individual CLs, marginalizing over all the foreground parameters at the map level using Gibbs sampling algorithm. One thing also is, since we're not delivering polarized data, we used the WMAP 9-year likelihood, at least the polarized part of it, and to make it uncorrelated or separate with the temperature, we have to correct the Q and U Stokes parameters from WMAP with the temperature map, and for that we use actually the Planck CMB temperature map. So of course all of that was, as shown before, tested extensively on simulations. One example that was shown before is basically how the mask was designed and validated on the full focal plane simulations. The mask was done using a thresholding both on foreground recovered components and on the residual chi-square maps. And so that allowed to keep a very large fraction of the sky for those low multiples, is about 87%. So that was shown also before. A very robust spectrum is obtained using different possible component separation methods, which are shown. In blue is the commander, which is used in the low L likelihood, basically. And in red, green, and magenta are the other component separation methods compared to WMAP. So well, we see that there is some, we see first of all the same spectra, which is nice with WMAP, but we do seem to see a 2% to 3% trend between the two spectra. So if we combine the two likelihoods, this is the best power spectrum we get for the CMB on our Planck data. And in green is the best fit for the lambda CDM model, which is in a very remarkable agreement, except maybe something at low L, which if we wanted to see if this is this was really a very good fit at low L. So the idea is we equip the best fit lambda CDM theoretical model with an extra amplitude and tilt, and we show here the posterior 1 and 2 sigma contours for either WMAP using WMAP likelihood or the Planck likelihood. So both tend to give slightly lower amplitude than 1 for an L max of 30. And because of the difference between the WMAP and Planck spectra, this is a little bit more sensitive, significant for the Planck data. Another way to see that is here, where we marginalize over the tilt and we vary the maximum L max, and we see that basically what we're seeing is our points in the spectra are a bit low at the 10% level compared to the best fit lambda CDM spectrum for the first 30 multiples or so. But this difference tends to go away as we increase the L max. So a lot will be said on cosmology this afternoon, so I think everybody is hungry, so we'll just stop here and thank you.
Thank you, and we got something to wonder about here also. Shalou?
It's more a remark than a question, but in what Simon has shown on the importance of the foreground, we can see a difference with what Charles was talking about. Charles mentioned the best frequency for the diffuse foregrounds, for example, and you can see there in the present presentation that the best for the IL, which is for which you are fighting, in fact, the point sources, and the radio point sources are dominating all the way to 200 gigahertz, the best is the 143 and not that. Furthermore, which is obvious, there is also a difference with the mask you are using. So I just wanted to point out that this business about optimizing the foreground and what you do is really dependent on the mask, on the L range, diffuse or point sources, and it's depending on what you want to do, the optimum is not at the same place.
Any more questions? Everybody hungry? I think we'll thank all the speakers of this morning's sessions again. Yeah, there's now lunch, and we return here at 2 o'clock precisely.